Beneath Europa's frozen surface lies something that shouldn't exist. A liquid ocean in the deep freeze of outer space, warmed by forces that would tear apart anything smaller than a moon. This water has been flowing for billions of years, never seeing sunlight, possibly never knowing life, or teeming with creatures we can't even imagine. Arthur C. Clarke declared this world off-limits in his fiction, but the real barriers are far more daunting than even he thought. Radiation levels that would kill in minutes, ice shells thick enough to bury mountains, distances that make Mars look like a neighborhood stroll, and an ocean so deep it dwarfs the Mariana Trench. Tonight, we explore why NASA spent $6 billion to study the terrifying world of Europa, and why the moon's hidden ocean might reveal the answer to the holy grail of space exploration. What if there actually is life out there? Prepare yourselves. We begin. Part 1. The Forbidden Moon. All these worlds are yours, except Europa. Attempt no landing there. Arthur C. Clarke didn't just write science fiction, he wrote prophecy. In 2010, Odyssey 2 and its 1984 film adaptation, this haunting warning echoes from the monoliths themselves, ancient guardians protecting Europa as a nursery for nascent life. But here's where fiction becomes uncomfortably prescient. Europa, Jupiter's fourth largest moon, really is one of the most promising places for life in our solar system. Not because of mystical monoliths, but because beneath its frozen surface lies something far more extraordinary, a global ocean containing more water than all of Earth's seas combined. Picture Europa through Voyager's first glimpse in 1979, a world unlike anything we'd seen, no ancient cratered moonscape here. Instead, a surface carved with what scientists call lineae, long, dark streaks and ridges crisscrossing the ice like some cosmic calligraphy. These aren't random scratches. They're stress fractures in a shell that moves, shifts, and renews itself. The ice is geologically young, mere tens of millions of years old, in a 4.5 billion-year-old solar system. What could keep Europa's surface so fresh? The answer lies in that hidden ocean, locked beneath 10 to 25 kilometers of ice. This isn't a frozen wasteland. It's an active world, flexed and heated by Jupiter's immense gravity, maintaining liquid water in permanent darkness. The stakes here go far beyond one moon. If life arose independently on Europa, separate from Earth's genesis, it would shatter our understanding of biology itself. It would suggest that life isn't a cosmic accident, but an inevitable consequence of the right conditions. Suddenly, every ocean world becomes a potential biosphere, every hidden sea, a possible nursery. But Europa guards its secrets jealously. The same radiation that might create the chemistry for life would kill any unprotected visitor in hours. The ice shell that preserves the ocean also conceals it from our instruments. And the moon's location, trapped in Jupiter's magnetic grip, makes it one of the most challenging destinations in the solar system. That's why NASA built Europa Clipper, not to land on this forbidden world, but to orbit Jupiter and steal glimpses of Europa's secrets through nearly 50 carefully planned flybys. It's a mission designed around limitations, threading the needle between scientific ambition and harsh physical reality. The word forbidden here carries no mystical weight. It means scientifically precious and brutally difficult to reach. Yet the unknowns lurking beneath Europa's ice remain genuinely unsettling. We're not just exploring a moon, we're potentially approaching our first contact with an alien biosphere. Europa Clipper will hunt for the ingredients of habitability, liquid water, essential chemicals, energy sources, and a stable environment over geological time. The mission won't detect life directly. That would require landing, drilling, and sampling techniques still years in development. Instead, it will answer a more fundamental question: could Europa support life as we know it? The themes we'll explore span the breadth of astrobiology, that hidden ocean, warmed by tidal friction and possibly enriched by minerals from a rocky seafloor, possible geysers that might spray ocean chemistry into space, offering tantalizing samples without the need for drilling. The complex dance of radiation chemistry at the surface, potentially creating both the building blocks and the energy sources that life requires. And the profound ethical questions that arise when we consider actually touching down on a world that might be alive. We must acknowledge the uncertainties up front. Europa's supposed plumes remain sporadic and contested, glimpsed by Hubble, hinted at by old Galileo data, but never definitively confirmed. The thickness of the ice shell, the chemistry of the ocean, the presence of hydrothermal vents, all remain educated speculation based on limited evidence. But that's precisely what makes Europa Clipper so crucial. We're not just sending instruments to a distant moon, we're dispatching our proxy to test one of the most profound questions in science. Are we alone? And if we're not, what does that mean for everything we thought we knew about life, intelligence, and our place in the cosmos? Clarke's fictional warning has become our scientific mandate: approach with reverence, study with care, and prepare for answers that might change everything. Part 2. The Terrifying Mission. Meet Europa Clipper. On October 14, 2024, something unprecedented lifted off from Kennedy Space Center. Strapped to a SpaceX Falcon Heavy rocket, Europa Clipper began its journey to Jupiter, the largest planetary science spacecraft NASA has ever built, carrying humanity's most sophisticated tools to investigate an alien ocean. Today, August 28, 2025, we're roughly 1,687 days away from Europa Clipper's arrival at Jupiter on April 11, 2030. That's over 4.5 years of cruise time, a reminder of just how far we're reaching into the cosmos. Deep space exploration isn't measured in months, it's a generational commitment. But why such an enormous, expensive machine for one moon? Europa Clipper spans roughly 30 meters, with its solar arrays deployed, about the size of a basketball court. It's a monument to engineering necessity. This far from the sun, solar panels must be massive to collect enough power. Jupiter's radiation environment demands heavy shielding, and the science payload requires precision instruments that can function in one of the most hostile environments in the solar system. The mission's price tag reflects its ambition, approximately $5 to $5.2 billion, making it one of NASA's most expensive planetary science missions ever conceived. Only the proposed Mars sample return mission would exceed this cost. Europa Clipper represents what NASA calls a large strategic flagship mission, the kind of project that defines an entire decade of exploration. The spacecraft won't orbit Europa itself. That would be suicide. Instead, it will orbit Jupiter and perform 49 carefully choreographed close flybys of Europa, each one lasting mere hours but potentially revealing secrets locked away for billions of years. This flyby strategy isn't a compromise, it's survival. Europa sits deep within Jupiter's radiation belts, where energetic particles would fry unshielded electronics and prove lethal to any human visitor within hours. Think of Europa Clipper as an armored reconnaissance vehicle. Its central electronics vault is constructed from aluminum alloy walls roughly 10 millimeters thick, a miniature bunker designed to protect the spacecraft's brain from radiation that would destroy conventional satellites. Every instrument, every computer, every circuit has been hardened against an environment that makes nuclear reactor cores seem hospitable. The mission architecture reflects this harsh reality. Rather than camping out in Europa's radiation-soaked neighborhood, Clipper will swoop in from safer distances, collect its data during brief encounters, then retreat to analyze and transmit its findings. It's like a series of high-speed photograph sessions with a subject that can't be approached safely. But what exactly is Clipper hunting? Not life itself, that distinction is crucial. The mission is designed to assess habitability, to determine whether Europa has the ingredients necessary to support life as we know it. Direct life detection would require landing on Europa's surface, or, even more ambitiously, drilling through kilometers of ice to reach the ocean below. Those missions remain concepts for future decades. Getting to Jupiter requires a carefully planned celestial ballet. Clipper's trajectory includes gravity assists from Mars in 2025 and Earth in 2026. using the gravitational pull of these worlds to accelerate the spacecraft without burning additional fuel. It's a 5.5-year journey that showcases the patience required for interplanetary exploration. The tour design itself is a masterpiece of orbital mechanics. Those 49 flybys will sample Europa from many different latitudes and longitudes, building a global portrait from dozens of brief encounters. Some passes will skim as close as 25 kilometers above Europa's surface, closer than the International Space Station orbits above Earth. Others will observe from greater distances, providing regional context for close-up discoveries. Each flyby presents a unique opportunity. Different viewing angles, different lighting conditions, different chances to spot active phenomena like possible plumes or fresh geological features. The spacecraft's instruments must work in perfect coordination, like a symphony orchestra where every musician gets only seconds to play their part. Consider the operational complexity. Clipper must survive not just Jupiter's radiation, but the gravitational tugs of Jupiter's 4 largest moons, the variable solar illumination at 5 astronomical units from the Sun, and the communication delays that place the spacecraft over 30 minutes away from Earth at light speed. Every command must be planned well in advance. Every observation sequence represents months of preparation. Yet for all its technical sophistication, Europa Clipper embodies something profoundly human: our compulsive need to explore, to know, to answer the questions that keep us awake at night. We've built this machine not just to study a moon, but to test whether we're alone in the universe. And if we're not alone, if Europa harbors even microbial life, everything changes. Our understanding of biology, of planetary science, of our cosmic significance would never be the same. The terrifying part isn't the radiation or the distance or the complexity. It's the possibility that we might actually find what we're looking for. Part 3. The Alien Ocean World. What's beneath the ice? Imagine an ocean with no surface, no waves, no sunlight, just eternal darkness beneath a shell of ice kilometers thick. This isn't science fiction. It's Europa, where the best current evidence suggests a global ocean lies hidden beneath 10 to 25 kilometers of frozen water. To put that in perspective, Europa's ice shell is roughly twice as thick as Mount Everest is tall. But beneath that frozen fortress lies something extraordinary, an ocean 60 to 150 kilometers deep. Earth's deepest ocean trench, the Challenger Deep, extends barely 11 kilometers below sea level. Europa's ocean could swallow Earth's deepest places and still have room for more water than all our planet's seas combined. The numbers are staggering. Europa, despite being smaller than Earth's moon, may contain 2 to 3 times as much water as all of Earth's oceans. It's a water world masquerading as a frozen wasteland, and that deception has protected its secrets for billions of years. But this isn't fresh water frozen in cosmic ice. The ocean is almost certainly salty, rich in sodium chloride and other dissolved minerals that make it electrically conductive. We know this because of Europa's magnetic signature, a time-varying field detected by NASA's Galileo spacecraft that betrays the presence of an electrically conductive fluid moving within Jupiter's powerful magnetosphere. Recent observations from the James Webb Space Telescope have revealed carbon dioxide concentrated in Europa's youngest geological features, particularly in a region called Terra Regio. This isn't just frozen atmospheric CO2 scattered randomly across the surface. The carbon dioxide correlates with areas where the ice appears freshly disrupted, suggesting material from the interior ocean has recently reached the surface. Laboratory experiments have reproduced similar chemistry. When researchers bombard sodium chloride with radiation similar to Jupiter's environment, they create the same yellowish-brown coloration we observe on Europa's surface. The moon's distinctive rust-colored streaks aren't rust at all. They're likely irradiated salts and sulfur compounds, chemical signatures of an active interface between ocean and space. Europa's surface tells a story of restless motion. Few impact craters mar its face, despite billions of years in a debris-filled solar system. The surface is geologically young, perhaps only tens of millions of years old. Instead of craters, Europa displays a complex tapestry of ridges, bands, and chaos terrains that speak of internal forces constantly reshaping the world. These aren't subtle geological processes playing out over millions of years. Europa's ice shell appears to be in motion, driven by tidal forces that flex and crack the frozen surface with each 85-hour orbit around Jupiter. The same gravitational dance that keeps Europa's orbit elliptical also keeps its interior warm, preventing the ocean from freezing solid, despite being 5 times farther from the Sun than Earth. Consider the energy budget. Jupiter's gravity doesn't just pull on Europa, it stretches and squeezes the entire Moon as Europa's distance from the gas giant varies throughout its orbit. This tidal heating generates enough energy to maintain liquid water and drive geological activity. It's a cosmic engine that's been running for billions of years, powered by orbital mechanics rather than stellar radiation. The surface colors provide additional clues to the hidden ocean's chemistry. Those distinctive brown and red streaks aren't just radiation damage. They're potentially oceanic materials that have been processed by Jupiter's harsh environment. When ocean water reaches the surface through cracks or upwelling, radiation breaks apart water molecules and alters dissolved salts, creating the complex chemistry we observe from space. But enormous questions remain. How thick is the ice shell exactly? Does it vary by location? What's the ocean's salinity, pH, and circulation pattern? Are there pockets of liquid water within the ice itself, creating a layered system of brine lenses and aquifers? Europa Clipper's instruments are specifically designed to answer these questions. Ice-penetrating radar will attempt to map the shell's thickness and internal structure. Magnetometry will constrain the ocean's depth and conductivity. Spectrometers will analyze surface chemistry to infer oceanic composition. Think of Europa as an entire world turned inside out. Instead of oceans on the surface and solid rock beneath, Europa hides its seas under an impenetrable ice shell, while its rocky mantle remains in contact with liquid water at the ocean floor. It's a configuration that might actually favor the emergence of life, protecting any organisms from radiation while maintaining the chemical interactions between water and rock that could drive biological processes. We're not just studying another moon. We're investigating an entirely alien class of world, an ice-covered ocean planet where life, if it exists, would have evolved in permanent darkness, fed by chemistry rather than sunlight, adapted to pressures and conditions unlike anything on Earth. The alien ocean world beneath Europa's ice may be the most habitable place in the solar system beyond Earth, and we're about to find out. Part 4. How Clipper will search for life indirectly. Europa Clipper isn't hunting for life directly, it's building the case for life's possibility. 9 sophisticated instruments will work together, like detectives gathering evidence, each one designed to answer specific questions about Europa's habitability. The Europa imaging system serves as Clipper's eyes, capturing both wide-angle regional views and narrow-angle close-ups with resolution down to 0.5 meter per pixel. But these aren't just pretty pictures. EIS will hunt for fresh surface deposits, map geological features that might indicate recent activity, and search for potential plume fallout, traces of ocean material that might have been ejected into space and fallen back to the surface. Reason: the radar for Europa assessment and sounding, ocean to near surface, represents perhaps the mission's most ambitious instrument. This dual-frequency ice-penetrating radar system can essentially X-ray Europa's ice shell, probing internal structure without drilling a single hole. Reason operates like subsurface sonar, sending radio waves through the ice and analyzing the echoes that bounce back from internal features. The radar might detect the boundary between the ice shell and the underlying ocean. It could map pockets of liquid water or brine lenses within the ice itself. Most intriguingly, Reason might identify the best places for future missions to drill, regions where the ice is thinnest or where liquid water lies closest to the surface. MISE, the Mapping Imaging Spectrometer for Europa, will create a global chemical atlas of Europa's surface. This instrument can identify specific minerals, salts, organic compounds, and hydrated materials by analyzing how different wavelengths of light are absorbed or reflected. MISE will map the distribution of Europa's distinctive surface colors, potentially revealing where oceanic materials have reached the surface most recently. Europa UVS, the ultraviolet spectrograph, searches for the faintest traces of water vapor and other gases in Europa's thin atmosphere. If Europa experiences sporadic plume activity, jets of water vapor erupting through surface cracks, UVS might catch these events in action. The instrument can also study auroral glows created when Jupiter's magnetic field interacts with Europa's atmosphere. MASSPEX, the mass spectrometer for planetary exploration, Europa, acts as Clipper's nose, designed to sniff and identify gases and particles in Europa's vicinity. If the spacecraft flies through a plume during one of its close encounters, MASSPEX could analyze the chemical composition of ejected ocean material. The instrument can identify organic compounds, measure isotopic ratios that might hint at biological processes, and characterize the chemical environment of Europa's hidden sea. SUDA, the surface dust analyzer, complements MASSPEX by examining solid particles, ice grains, and dust kicked up from Europa's surface or ejected in plumes. Like a cosmic microscope, SUDA can determine the molecular composition and isotopic signatures of individual grains, potentially reading the chemical history of Europa's ocean written in microscopic ice crystals. The magnetometer and plasma instruments work as a team to probe Europa's interior structure. By measuring how Jupiter's powerful magnetic field induces electrical currents in Europa's conducting ocean, these instruments can constrain the ocean's depth, salinity, and thickness of the overlying ice shell. They can also separate the effects of Europa's ocean from the complex plasma environment surrounding Jupiter. What makes Clipper's approach truly powerful is the convergence of multiple instruments on the same targets. Imagine a flyby that detects a warm spot with the thermal imager, fresh salts with the spectrometer, and a possible shallow water pocket with the radar. That combination of evidence would mark a high-priority site for detailed investigation, perhaps even a target for future landing missions. Each instrument has been hardened to survive Jupiter's radiation environment while maintaining the precision necessary to detect subtle chemical signatures. The entire payload represents decades of technological development, miniaturizing laboratory-quality instruments to operate autonomously in the outer solar system. But Clipper's indirect approach serves a crucial purpose beyond technical necessity. Before we contemplate landing on Europa or drilling through its ice, we need to understand what we're dealing with. Is the ice shell uniform or variable? Where might the ocean be most accessible? What's the chemical environment like? Are there active processes that could transport surface materials to the ocean or ocean materials to the surface? These questions matter enormously for planetary protection, the protocols designed to prevent contamination of potentially habitable worlds. If Europa harbors life, we have a responsibility to study it without destroying it. That requires knowing where life might exist, how it might be distributed, and how our presence could affect indigenous ecosystems. Clipper's mission represents a new paradigm in astrobiology: systematic, patient, comprehensive characterization of entire worlds before we take the irreversible step of physical contact. We're not just exploring Europa, we're learning how to explore ocean worlds responsibly. The terrifying reality is that Clipper might actually succeed. It might confirm that Europa has all the ingredients for life, locate the best places to search for organisms, and build an irresistible case for direct investigation. And then we'll face the truly difficult questions: should we land? Should we drill? And are we prepared for what we might find? Part 5. Evidence so far, from Voyager to Galileo and Juno, JWST. The search for Europa's secrets began with a photograph. In 1979, Voyager 1 captured the first detailed images of Jupiter's fourth largest moon, revealing a world that defied every expectation. Where planetary scientists expected ancient cratered terrain, the standard signature of a dead, airless world, they found something unprecedented, a smooth, bright surface carved with long, dark lines that looked disturbingly organic. These weren't the random scars of cosmic bombardment. Europa's lineae formed patterns suggesting global-scale processes, stress fractures in a surface that seemed young, active, and fundamentally different from any world previously explored. The moon's brightness indicated water ice, but the lack of craters suggested that surface was constantly renewed. Something was erasing Europa's impact history as fast as the solar system could create it. Voyager's images raised more questions than they answered, but they established Europa as a world worth returning to. That return came with the Galileo mission, launched in 1989 and arriving at Jupiter in 1995. Galileo would spend 8 years studying the Jovian system, revolutionizing our understanding of Europa with each passing orbit. The breakthrough came from Galileo's magnetometer. As the spacecraft flew past Europa, it detected something extraordinary, a magnetic field that varied in strength and direction in sync with Jupiter's 11-hour rotation. This wasn't Europa generating its own magnetic field like a miniature planet. Instead, it was evidence of electrical currents flowing through a conducting layer within the moon. The physics are elegant and unmistakable. Jupiter's powerful magnetic field sweeps past Europa, inducing electrical currents in any conducting material within the moon. Rock doesn't conduct electricity well enough to explain the observations, but a salty ocean would create exactly the magnetic signature Galileo detected. The time-varying field became Europa's signature, electromagnetic proof of a hidden sea. Galileo's cameras mapped Europa's surface in unprecedented detail, revealing the complex geology of ridges, bands, and chaos terrains that spoke of ice in motion. Some regions showed evidence of what looked like plate tectonics in ice, chunks of surface that had broken apart, shifted, and refrozen in new configurations. The images suggested a shell of ice floating on liquid water, flexed and cracked by tidal forces. But Galileo held one more secret, hidden in its data for 2 decades. In 2018, scientists reanalyzing old magnetometer and plasma wave measurements realized that Galileo had likely flown through a Europa water plume during a close flyby in December 1997. The spacecraft had detected magnetic and plasma anomalies consistent with passing through a cloud of charged water particles, potential direct sampling of Europa's ocean. The Hubble Space Telescope added another layer of evidence starting in 2012. Multiple observations suggested sporadic water vapor plumes erupting from Europa's south polar region, reaching heights of up to 200 kilometers. These weren't continuous geysers like those at Saturn's moon Enceladus, but intermittent events that appeared to correlate with Europa's orbital position and tidal stresses. However, Europa's plumes proved frustratingly elusive. Later, Hubble observations failed to consistently reproduce the initial detections, leading to ongoing debates about their reality, frequency, and locations. The plumes became Europa's most tantalizing and controversial feature, potentially offering direct access to ocean chemistry, but refusing to perform on cue. More recent observations have added crucial pieces to Europa's puzzle. The James Webb Space Telescope's 2023 detection of carbon dioxide in Tara Regio provided the first definitive evidence of ocean-derived chemistry reaching Europa's surface. The CO2's concentrations correlated with geologically young terrain, suggesting recent transport from the interior ocean to the surface. Ground-based spectroscopy and laboratory experiments have identified sodium chloride, table salt, in Europa's youngest surface features. When researchers bombard salt with radiation similar to Europa's environment, they reproduce the distinctive yellow-brown colors observed on the moon's surface. The chemistry matches. Europa's ocean appears to be salty, and that salt reaches the surface where radiation alters its appearance. NASA's Juno mission, while primarily focused on Jupiter itself, has provided additional context for Europa's radiation environment and magnetic interactions. Juno's measurements help constrain models of how radiation processes modify surface chemistry and how Jupiter's magnetic field penetrates Europa's interior. Even as evidence mounts for Europa's subsurface ocean, major uncertainties remain. The ice shell's thickness remains poorly constrained, with estimates ranging from a few kilometers to several tens of kilometers. The ocean's exact composition, circulation patterns, and interaction with the underlying rocky mantle remain speculative. The frequency and distribution of possible plume activity continue to puzzle researchers. But the cumulative evidence paints a compelling picture. Europa hosts a global ocean beneath its ice shell. That ocean is salty and potentially chemically active, and materials from the ocean occasionally reach the surface where we can study them remotely. Each new observation adds detail to this portrait while raising new questions about Europa's habitability. The progression from Voyager's first glimpse to today's sophisticated analysis represents 4 decades of patient detective work. We've gone from recognizing Europa as unusual to understanding it as potentially habitable. The next phase, Europa Clipper's comprehensive survey, will determine whether that potential translates into actual conditions suitable for life. What we've learned so far suggests Europa isn't just another moon. It's a world where the ingredients for life may have been mixing in the dark for billions of years. Whether anything emerged from that chemistry remains the greatest mystery in our solar system. Part 6. Plumes, Geysers, Europa's possible ocean spray. Picture this: jets of water vapor and ice crystals erupting through cracks in Europa's surface, blasting ocean chemistry directly into space at speeds of several hundred meters per second. It sounds like science fiction, but it might be happening right now, offering us a cosmic gift, direct samples of an alien ocean without the need to drill through kilometers of ice. These aren't the reliable geysers of Yellowstone or even the predictable plumes of Saturn's moon Enceladus. Europa's potential plumes are sporadic, elusive, and maddeningly inconsistent. They represent one of the most important unresolved questions in planetary science. Does Europa regularly vent its ocean contents into space? The story begins with the Hubble Space Telescope's surprising observations in 2012 and 2016. Using ultraviolet spectroscopy, researchers detected what appeared to be water vapor signatures rising from Europa's southern polar regions, reaching heights of up to 200 kilometers above the surface. These weren't subtle signals. The modeled plume heights exceeded the altitude of the International Space Station above Earth. But Europa's plumes refused to cooperate with follow-up observations. Subsequent Hubble campaigns often found nothing, leading to heated debates about the reality, frequency, and locations of these enigmatic eruptions. Unlike Enceladus, where Cassini observed consistent plume activity over years of observations, Europa seemed to play hide-and-seek with its geysers. The plot thickened in 2018 when researchers reanalyzing Galileo data from 20 years earlier found evidence that the spacecraft had likely flown through a plume during its closed December 1997 flyby. Magnetic field and plasma wave measurements showed anomalies consistent with passing through a cloud of charged water particles. Galileo had potentially sampled Europa's ocean chemistry without anyone realizing it at the time. If Europa's plumes are real, they represent an extraordinary opportunity for astrobiology. Rather than landing on the surface or drilling through the ice shell, a spacecraft could potentially sample ocean material simply by flying through the erupted spray. This is exactly what Cassini accomplished at Enceladus, detecting organic compounds, hydrogen gas, and evidence of seafloor chemistry in the geyser plumes. Europa Clipper's instruments are specifically designed to capitalize on any plume encounters. MassSpecs, the mass spectrometer, can identify gases and ionized particles with extraordinary precision. If Clipper flies through a plume, MassSpecs could determine the chemical composition of Europa's ocean water, detect organic molecules, and measure isotopic ratios that might hint at biological processes. SUDA, the dust analyzer, would complement MassSpecs by examining solid particles, ice grains, and any entrained materials ejected from the ocean. These microscopic samples could carry chemical fingerprints of Europa's seafloor, dissolved organic compounds, or even more complex chemistry that develops in the ocean's depths. The speculation about what plumes might reveal is tantalizing, though we must label it clearly as speculation. If Europa's ocean hosts hydrothermal vents like those on Earth's seafloor, plume chemistry might include hydrogen sulfide, hydrogen gas, and dissolved minerals that betray active water-rock interactions. If life exists in Europa's ocean, its metabolic byproducts might be detectable in erupted materials, but Europa is not Enceladus. The two moons operate under different physical conditions that could dramatically affect plume behavior. Europa's higher gravity means that ejected materials fall back to the surface more quickly. Its thicker ice shell might require more energy to breach, and its position within Jupiter's intense radiation environment could alter plume chemistry through radiolysis, the breakdown of molecules by energetic particles. The mechanics of Europa's potential plumes remain poorly understood. On Enceladus, tidal heating appears to drive plume activity through tiger stripe fractures near the South Pole. Europa's plume sources, if they exist, might be more widely distributed and tied to the global pattern of lineae, the long cracks that crisscross the moon's surface. One intriguing possibility is that Europa's plumes are intermittent because they're tied to tidal cycles. As Europa orbits Jupiter every 85 hours, varying gravitational stresses might open and close conduits between the ocean and surface. This could explain why Hubble sometimes detects plume activity and sometimes doesn't. The observations might be catching Europa at different phases of its tidal cycle. The implications extend beyond Europa itself. If ocean worlds regularly vent their contents into space, it opens new possibilities for exploring other icy moons like Ganymede, Callisto, and even distant targets like Pluto's moon Charon. Rather than requiring complex drilling missions, we might be able to characterize alien oceans through orbital surveys that sample naturally occurring eruptions. Europa Clipper will settle the plume question once and for all. Its multiple instruments will monitor for plume activity during each flyby, ready to analyze any encountered materials. The spacecraft's trajectory is designed to provide multiple opportunities for plume detection, with close approaches at various latitudes and longitudes. But here's the unsettling reality. If Clipper confirms active plume venting and detects complex organic chemistry in the ejected materials, it will transform Europa from an interesting moon into humanity's first confirmed contact with an alien chemical environment. We'll be holding samples of another world's ocean, analyzing chemistry that developed in isolation for billions of years. The thought of flying through Europa's ocean spray, literally breathing the exhalations of an alien world, represents both the pinnacle of exploration and the beginning of profound new questions about our place in a universe that might be teeming with life. Part 7. A world that moves. Drifting ice. Planet. Scale shifts. Europa's ice shell doesn't just float on its hidden ocean, it wanders. Evidence suggests the entire frozen surface can drift relative to the moon's interior, sliding around like a loose skin on a cosmic orange. This isn't subtle geological creep playing out over millions of years. We're talking about ice tectonics on a planetary scale. The evidence comes from Europa's surface patterns themselves. Detailed mapping of lineae, those long, dark cracks crisscrossing the ice, reveals something extraordinary. Some features don't align with Europa's current tidal bulge. It's as if the surface remembers being in a different orientation, recording ancient stresses that no longer match the moon's present relationship with Jupiter. This phenomenon, known as non-synchronous rotation, suggests Europa's ice shell can slip relative to its rocky interior. Picture the moon as a layered system, a solid rock core, a liquid water ocean, and a floating ice shell. If the shell is decoupled from the interior by that intervening ocean, it could rotate at a slightly different rate, causing the surface to gradually drift over geological time. Even more dramatically, some researchers propose that Europa experiences true polar wander, wholesale shifts in the orientation of the entire ice shell. Major impacts, changes in ice thickness, or redistribution of mass could cause the surface to reorient itself, moving features that formed near the poles toward the equator and vice versa. But Europa's mobile ice tells an even more remarkable story. In 2014, a groundbreaking study suggested that Europa might be the only body in the solar system besides Earth to exhibit plate tectonics. The researchers identified surface features that looked remarkably like terrestrial subduction zones, places where one ice plate dives beneath another. The proposed ice tectonics operate on the same principles as Earth's plate system, but with crucial differences. Instead of solid rock plates moving over hot mantle, Europa's ice plates would float on liquid water, driven by tidal heating and convection. Old ice could be recycled into the ocean while new ice forms at spreading ridges, creating a dynamic system that renews the surface over millions of years. This isn't just academic speculation, it has profound implications for habitability. Moving ice plates could transport oxidants created by radiation at the surface down into the ocean, providing energy sources for potential life. Conversely, the system could bring ocean chemistry to the surface, creating opportunities for remote sensing of subsurface conditions. The chaos terrains scattered across Europa's surface tell their own story of mobility and violence. These regions look like broken puzzles, chunks of older surface that have been shattered, shifted, and refrozen in new configurations. Some chaos terrain blocks appear to have rotated relative to their surroundings, while others show evidence of having been partially dissolved and reformed. What could drive such dramatic surface disruption? The leading hypothesis involves density-driven overturn. If warm, less dense material rises from the ocean while cold, dense ice sinks, the result could be catastrophic disruption of the existing surface. It's like watching a slow-motion explosion captured in ice, playing out over thousands of years. The mechanisms driving Europa's ice motion remain hotly debated. Tidal flexing provides obvious energy, but the details of how that energy translates into surface motion are complex. The thickness of the ice shell matters enormously. A thin shell would be more mobile but less stable, while a thick shell might resist motion but store more tidal energy. Europa Clipper's ice-penetrating radar will provide crucial constraints on these processes. By mapping ice thickness variations and internal structure, reason can test whether Europa's shell is uniform or layered, thick or thin, solid or partially molten. The magnetometer will help determine how well the ocean couples to the ice shell, constraining models of rotational decoupling. The implications extend far beyond geology. If Europa's ice shell is mobile, it creates a dynamic interface between the irradiated surface and the protected ocean. This could establish chemical gradients and mixing processes that don't exist on static worlds. The moving ice might create oases where surface oxidants concentrate, or niches where ocean chemistry remains fresh and accessible. Consider the temporal scales involved. If Europa's surface drifts at rates comparable to Earth's plate tectonics, centimeters per year, then major reconfigurations could occur over millions of years. Features we see today might have formed at entirely different latitudes. The chemical signatures we detect might represent ancient ocean chemistry that's been transported thousands of kilometers from its origin. This mobility poses fascinating challenges for future exploration. Landing sites that appear geologically interesting today might not represent current ocean chemistry. Conversely, seemingly bland regions might conceal recently exposed ocean materials. Understanding Europa's ice dynamics becomes crucial for planning where to look for signs of life. The moving ice also raises intriguing possibilities for life itself. On Earth, plate tectonics plays a crucial role in regulating climate and recycling nutrients. Europa's ice tectonics might serve similar functions, maintaining chemical gradients and energy flows that could support biological processes. The dynamic interface between ice and ocean might create ecological niches that don't exist on static worlds. Perhaps most unsettling is the realization that Europa's surface is not a historical record but a palimpsest, a manuscript that's been written, erased, and written again countless times. The world we're preparing to study is not the world that existed a million years ago. We're investigating a living, breathing planet where yesterday's ocean chemistry might be tomorrow's surface geology, and the ground beneath any future lander's feet might be moving at speeds we can barely measure but cannot ignore. Part 8. Jupiter's Deadly Grip, the Radiation Gauntlet. Europa orbits within one of the most lethal environments in the solar system. Jupiter's magnetic field traps charged particles, electrons and ions accelerated to tremendous energies, creating radiation belts that make Earth's Van Allen belts look benign. A human standing unprotected on Europa's surface would receive a fatal dose of radiation in less than a day. Put that in perspective. The radiation environment near Europa delivers doses measured in thousands of rads per day. For comparison, a chest X-ray exposes you to about 0.1 rads. A worker in a nuclear power plant is limited to 5 rads per year. Europa's neighborhood would kill you faster than standing next to an unshielded nuclear reactor. This isn't just a hazard for hypothetical human visitors. It's an engineering nightmare for robotic explorers. High-energy particles penetrate spacecraft walls, flip bits in computer memory, degrade solar panels, and gradually destroy electronic components. Every circuit, every sensor, every computer chip must be hardened against an environment that would fry consumer electronics in minutes. Europa Clipper's solution is elegant in its brutality: armor. The spacecraft's most sensitive electronics are housed in a titanium and aluminum vault, roughly the size of a large suitcase. The walls are approximately 10 millimeters thick, not much by terrestrial standards, but sufficient to reduce the radiation dose to levels that hardened electronics can survive for years. But even hardened components have limits. That's why Clipper won't orbit Europa directly. Instead, it will orbit Jupiter and make brief, carefully planned passes through Europa's radiation environment. Each flyby exposes the spacecraft to intense radiation for hours, but then Clipper retreats to safer distances where it can process data, communicate with Earth, and prepare for the next encounter. Think of it as a series of high-speed reconnaissance missions into enemy territory. Clipper will swoop through Europa's neighborhood, collect as much data as possible, then escape before the radiation can cause permanent damage. Over the course of its mission, the spacecraft will accumulate a total radiation dose equivalent to several million chest X-rays. The mission's radiation engineers had to consider every component, every wire, every solder joint. Standard computer chips are replaced with radiation-hardened versions that can function after exposure to particle bombardment. Memory systems include error correction codes that can detect and fix radiation-induced data corruption. Even the spacecraft's cameras use special sensors designed to maintain image quality despite constant particle hits. Europa Clipper carries a radiation monitor, essentially a dosimeter that tracks the spacecraft's exposure throughout the mission. This instrument doesn't just protect the spacecraft, it advances our scientific understanding of Jupiter's radiation environment. Future missions will benefit from Clipper's detailed mapping of the radiation hazards around Europa. The irony is profound. The same radiation environment that threatens our spacecraft also drives chemistry that might support life. High-energy particles don't just destroy electronics, they split water molecules, break apart other compounds, and create reactive species that wouldn't exist otherwise. Europa's surface chemistry is fundamentally shaped by this constant particle bombardment. Every impact creates a cascade of chemical reactions. Water ice splits into hydrogen and oxygen. Sulfur compounds from Jupiter's volcanic moon Io get embedded in Europa's surface. Salt crystals are altered and discolored. The result is a complex cocktail of chemicals that gives Europa its distinctive appearance and might provide energy sources for life in the ocean below. But radiation chemistry is a double-edged sword. While it creates potentially useful oxidants and reactive species, it also destroys complex organic molecules that life might need. Any organic compounds reaching Europa's surface face immediate bombardment by particles that can break molecular bonds and scramble chemical structures. This creates a race against time for any surface processes. Fresh organic materials ejected from the ocean in hypothetical plumes would need to be detected quickly before radiation degrades them beyond recognition. It's one reason why Europa Clipper's instruments must be so sensitive. They're looking for chemical signatures that might be erased within years or decades of surface exposure. The spacecraft's operational choreography reflects these constraints. Instrument duty cycles are carefully planned to maximize data collection while minimizing exposure time. Some observations require multiple flybys to build up sufficient signal, since single passes through the radiation environment limit how long instruments can operate. Future missions face even greater challenges. A Europa lander would need either heavy shielding that increases mass and complexity, or it would have to operate in shadowed regions where Jupiter's magnetic field provides some protection. A mission to drill through Europa's ice and reach the ocean would require technologies we're only beginning to develop, systems that can function in the radiation environment for months or years. The radiation environment also affects mission planning in subtle ways. Communication windows are limited by the spacecraft's need to retreat from Europa after each encounter. Data transmission rates are constrained by the need to use error correction protocols that can handle radiation-induced interference. Even the spacecraft's orbit is designed around radiation considerations rather than purely scientific objectives. Yet there's something almost poetic about humanity's approach to Europa. We're sending our most sophisticated robotic explorer into an environment that would be instantly lethal to its creators. We're using technology to peer into places where biology cannot venture, extending our senses across hundreds of millions of kilometers to investigate a world that kills with invisible radiation. Europa Clipper represents a new breed of exploration, not the romanticized vision of human pioneers stepping onto alien shores, but the reality of robotic proxies braving environments that would destroy us in moments. We're exploring not through physical presence, but through technological presence, using machines as our ambassadors to worlds we can never safely visit ourselves. The radiation that makes Europa so dangerous for visitors might be precisely what makes it interesting for life. And that paradox, that the same environment that threatens our technology might nurture alien biology, captures everything mysterious and compelling about this frozen moon orbiting in Jupiter's deadly embrace. Part 9. Radiation, Curse, and Blessing. The radiation that would kill a human visitor in hours might be precisely what keeps Europa's ocean alive. This isn't just cosmic irony, it's fundamental chemistry playing out on a planetary scale, transforming water and simple compounds into the complex molecules that life requires. Every high-energy particle that slams into Europa's surface splits water molecules through a process called radiolysis. The same radiation that destroys electronics creates hydrogen peroxide, oxygen, and other oxidizing compounds that rain down onto the ice in a constant chemical shower. These aren't trace contaminants. They're produced in quantities that could power entire ecosystems. Ground-based telescopes have directly detected hydrogen peroxide on Europa's surface, confirming that radiolysis is actively occurring today. The H2O toys concentrations aren't trivial. They represent a significant reservoir of chemical energy locked in Europa's ice. If this material finds its way into the ocean, it could serve as fuel for chemosynthetic life forms. But radiation chemistry produces more than just simple oxidants. The James Webb Space Telescope's detection of carbon dioxide in Europa's youngest terrain suggests that radiation is processing more complex chemistry, possibly involving organic compounds transported from the ocean to the surface. The CO2 correlates with geologically fresh features, implying recent chemical activity. Consider the energy budget. Europa receives approximately 100 times more high-energy radiation than Earth's surface. That bombardment doesn't just alter existing chemicals, it drives reactions that wouldn't occur otherwise, creating disequilibrium conditions that life could potentially exploit. It's like having a cosmic laboratory, constantly mixing new compounds and testing new reactions. The key question is transport. How efficiently do these radiation-produced chemicals reach Europa's ocean? The ice shell might act as a chemical conveyor belt, carrying surface oxidants downward through fractures, melting processes, or the ice tectonics we discussed earlier. If the transport is efficient, Europa's ocean could be chemically energized by surface processes occurring dozens of kilometers above. Conversely, the ocean might supply reducing compounds, hydrogen gas, organic molecules, dissolved minerals that react with surface-produced oxidants to release energy. This creates the possibility of chemical gradients spanning Europa's entire ice shell, with oxidized chemistry at the top and reduced chemistry at the bottom. Life thrives on such gradients. But radiation chemistry cuts both ways. The same processes that create potentially useful oxidants also destroy complex organic molecules. Any sophisticated chemistry, amino acids, nucleotides, lipids, faces immediate bombardment by particles that can break molecular bonds and scramble chemical structures. It's a constant battle between creation and destruction. Europa Clipper's instruments are specifically designed to map this chemical battlefield. MISE, the mapping spectrometer, will identify where different compounds concentrate on the surface. UVS, the ultraviolet spectrograph, can detect some of the gases produced by radiolysis. MASSPEX and SUDA will analyze any materials ejected from the surface, potentially revealing the products of radiation chemistry. The mission will also map variations in radiation dose across Europa's surface. Different regions experience different levels of particle bombardment depending on their magnetic shielding and exposure geometry. These variations could create chemical provinces with distinct compositions, some regions rich in oxidants, others where organic materials might survive longer. Recent laboratory experiments have revealed the complexity of radiation chemistry on icy surfaces. When researchers bombard Europa analog materials with particle beams, they create not just simple oxidants but complex organic compounds, including some that could serve as precursors to biological molecules. The ice acts as both a target and a reactor, concentrating and protecting chemistry that might be impossible in the vacuum of space. The timescales matter enormously. Europa's surface chemistry operates in real time, particle impacts occur constantly, chemical reactions proceed within seconds or minutes, and new compounds form and degrade on timescales we can observe. But the transport to the ocean might take thousands of years, creating a chemical pipeline that connects fast surface processes to the slow, deep chemistry of the hidden sea. This raises profound questions about detectability. If Europa's ocean hosts life, would its chemical signatures survive transport through the radiation-bombarded ice shell? Or would biological compounds be processed and altered beyond recognition by the time they reach the surface where our instruments can detect them? The answer might depend on timing and location. Fresh chemistry, materials recently transported from the ocean or recently processed by radiation, might retain detectable biological signatures. Older surface materials would show only the degraded end products of radiation processing. Europa Clipper's strategy of mapping surface age and chemistry simultaneously could identify the best targets for detecting ocean-derived materials. There's something almost alchemical about Europa's radiation chemistry, the transformation of simple starting materials into complex, potentially biological compounds through exposure to cosmic forces. Medieval alchemists sought the philosopher's stone that could transmute base metals into gold. Europa might host radiation chemistry that transmutes water and simple molecules into the building blocks of life. But the blessing comes with a curse. The same radiation that drives chemistry also erases evidence. Any signs of life reaching Europa's surface face immediate attack by particles that break apart delicate molecular structures. We're in a race against cosmic chemistry, trying to detect biological signatures before radiation destroys them. Europa Clipper will map this chemical battlefield in unprecedented detail, revealing where radiation creates potentially useful compounds, where chemistry might survive longest, and where future missions should look for signs of life. We're not just studying a moon, we're investigating a planet-sized chemistry experiment that's been running for billions of years. And the terrifying possibility remains. What if radiation chemistry has been feeding life in Europa's ocean for geological ages? What if we're about to discover that Jupiter's deadly radiation belts have been inadvertently nurturing an alien biosphere since the solar system was young? Part 10. Hydrothermal oases. Heat from below. Imagine the seafloor of Europa's hidden ocean, kilometers beneath ice, and hundreds of millions of kilometers from the sunday. No light has ever penetrated these depths. Yet this darkness might teem with chemistry and energy that could support entire ecosystems, powered not by stellar radiation, but by the heat of planetary formation and the physics of tidal friction. Europa's rocky mantle doesn't just provide a foundation for the ocean, it might actively feed it. As Jupiter's gravity flexes Europa through each 85-hour orbit, that tidal energy doesn't just warm the ice. It heats the rocky interior, potentially driving hydrothermal activity on the ocean floor. We're talking about underwater volcanoes, mineral-rich hot springs, and chemical reactions that could sustain life in permanent darkness. The physics are compelling. Tidal heating affects Europa's entire interior, not just the ice shell. The rocky mantle experiences stress and strain that generate heat through friction and deformation. This heat has to go somewhere, and the most likely destination is hydrothermal venting at the seafloor, underwater geysers that would make Yellowstone's features look modest. On Earth, hydrothermal vents host some of the most extreme and diverse ecosystems on the planet. These oases of life exist in conditions that would kill most surface organisms: crushing pressure, toxic chemistry, temperatures that can exceed 200 degrees Celsius. Yet vent communities thrive on chemosynthesis, using chemical energy instead of sunlight to power biological processes. The key reaction is often serpentinization, the interaction between seawater and certain types of rock that produces hydrogen gas, methane, and other organic compounds. This isn't exotic chemistry requiring rare materials. Serpentinization occurs whenever water contacts the right minerals at the right temperatures, and it generates exactly the kinds of reduced compounds that life can use for energy. Europa's ocean floor might be ideal for serpentinization. If the moon's rocky mantle contains the olivine and pyroxene minerals common in solar system bodies, contact with heated seawater could drive extensive water-rock reactions. The result would be hydrogen-rich fluids venting into the ocean, a chemical energy source that could support vast microbial ecosystems. Saturn's moon Enceladus provides a proof of concept. When NASA's Cassini spacecraft analyzed plume materials ejected from Enceladus's subsurface ocean, it detected hydrogen gas, organic compounds, and mineral particles consistent with hydrothermal activity. The chemistry suggested active water-rock reactions occurring on Enceladus's seafloor, creating conditions that could support life. Europa's hydrothermal potential might be even greater than Enceladus's. Europa is larger, with more rocky material and stronger tidal heating. The ocean is deeper and more stable. If hydrothermal venting occurs on Europa, it might be more vigorous and widespread than anything we've seen in the outer solar system. But Europa Clipper can't directly image hypothetical seafloor vents located beneath dozens of kilometers of ice and ocean. Instead, the mission will search for indirect evidence, chemical signatures that betray subsurface processes. The thermal infrared imager might detect warm spots on the surface that correlate with upwelling heated water. The spectrometers could identify minerals or chemical compounds that originate from water-rock reactions. Most intriguingly, if Europa experiences plume activity, MASPEX and SUDA could analyze ejected materials for chemical signatures of hydrothermal processes. Hydrogen gas, dissolved minerals, organic sulfur compounds, these would be smoking guns for active seafloor chemistry. The speculation about Europa's potential hydrothermal ecosystems is clearly speculation, but it's informed by what we know about life in extreme environments. If Europa hosts seafloor venting, the chemistry could support not just simple microbes but complex communities. Primary producers, organisms that harvest chemical energy, could form the base of food webs that include grazers, predators, and decomposers. The energy flux matters enormously. Earth's hydrothermal vents support biomass densities that can exceed those of tropical rainforests. If Europa's tidal heating drives similarly vigorous water-rock reactions, the chemical energy available could sustain rich biological communities despite the absence of sunlight. But Europa's conditions differ from Earth's in crucial ways. The ocean pressure might be higher, the chemistry different, the temperature gradients more extreme. We can't simply assume that Europa's hypothetical vents would resemble Earth's. They might host entirely alien forms of life adapted to conditions we can barely imagine. There's also the question of time. Hydrothermal activity on Earth is often episodic, with vent fields turning on and off over thousands of years. Europa's venting might follow similar patterns, creating oases that migrate across the seafloor as tidal heating shifts and changes. Life would need to adapt to or follow these moving energy sources. Europa Clipper will provide our first comprehensive assessment of Europa's potential for seafloor hydrothermal activity. The mission can't prove that vents exist, but it can determine whether the conditions are right and whether chemical evidence supports active water-rock reactions. The implications extend far beyond Europa. If ocean worlds regularly host hydrothermal activity, it opens vast territories for potential life throughout the solar system and beyond. Every icy moon with a subsurface ocean becomes a candidate for seafloor ecosystems. Every exoplanet with liquid water might harbor hydrothermal oases. But here's the truly unsettling possibility. If Europa's seafloor hosts active hydrothermal venting, and if that venting has been ongoing for billions of years, then we might be approaching our first contact with a mature alien biosphere. Not just microbes eking out existence in harsh conditions, but potentially complex ecosystems that have had geological time to evolve, diversify, and spread across an entire world. The darkness beneath Europa's ice might not be empty. It might be alive with chemistry, energy, and possibilities that would fundamentally change our understanding of life's potential in the universe. Part 11. What life could look like, from microbes to food webs. In Europa's lightless ocean, life wouldn't look like anything we recognize from Earth's sunlit biosphere. Forget green plants and blue skies. Here, in eternal darkness beneath kilometers of ice, life would be fundamentally alien, powered by chemistry instead of light, adapted to crushing pressure, and potentially organized in ways that would challenge our basic understanding of biology. The most conservative expectation is microbial life, bacteria, or archaea-like organisms that harvest chemical energy from the reactions we've discussed. These would be tiny, perhaps smaller than typical Earth bacteria, slow-growing, and incredibly tough. They might form biofilms on Europa's seafloor, extracting energy from mineral surfaces or dissolved chemicals in ways that leave minimal traces of their existence. But even simple microbes could leave detectable signatures if Europa Clipper manages to sample ocean materials through plume activity. Mass specs could identify organic compounds with isotopic ratios that betray biological processes. On Earth, life preferentially uses lighter isotopes of carbon and sulfur, creating chemical fingerprints that persist even after organisms die and decay. Life's impact on chemistry could be subtle but distinctive. Biological processes often create patterns in molecular ratios that purely chemical processes don't produce. Specific amino acids might appear in non-random combinations. Organic sulfur compounds might show isotopic signatures of metabolic activity. These would be indirect evidence, not organisms themselves, but the chemical shadows they cast. Europa's unique environment might drive unusual biochemistry. Earth's life is built around carbon, but Europa's chemistry includes abundant sulfur, potential methane production, and oxidant-reductant gradients that don't exist on Earth. Life adapting to Europa's conditions might use different molecular scaffolds, different energy storage systems, different approaches to maintaining cellular organization. The pressure environment alone could reshape biology. Europa's ocean might be under several times Earth's atmospheric pressure, not crushing by deep-sea standards, but enough to affect molecular structures and reaction rates. Proteins, membranes, and other biological components might need to be fundamentally different to function under these conditions. If Europa's ocean hosts hydrothermal vents, the possibilities expand dramatically. Vent ecosystems could support multiple trophic levels, primary producers that harvest chemical energy, consumers that feed on organic matter, predators that consume other organisms, and decomposers that recycle nutrients. The energy flux from active venting could sustain biomass densities comparable to Earth's most productive environments. Imagine layered ecosystems organized around different energy sources. Near hypothetical hydrothermal vents, thermophilic organisms might cluster around mineral-rich hot water. In the broader ocean, chemosynthetic microbes could harvest energy from dissolved compounds. At the ice-water interface, specialized organisms might exploit the unique chemistry created by radiation products filtering down from the surface. But we must be clear about the limits of speculation. Europa Clipper isn't designed to detect organisms directly. The mission will assess habitability, whether Europa has the ingredients and energy sources necessary to support life. Actually, finding living organisms would require landing on Europa, drilling through the ice, or developing technologies that can sample the ocean directly. The search strategy focuses on building blocks rather than biology. Clipper will map organic compounds, characterize chemical gradients, identify energy sources, and determine whether Europa maintains the stable conditions necessary for life over geological timescales. These are the prerequisites for biology, not biology itself. Yet even confirming habitability would be revolutionary. If Europa has all the ingredients for life, liquid water, organic chemistry, energy sources, and stable conditions, it would suggest that life-supporting environments might be common throughout the universe. The implications would cascade through astronomy, biology, and philosophy. The scariest possibility for many people isn't finding life, it's finding silence. What if Europa has perfect conditions for biology but remains sterile? That would suggest life requires something beyond chemistry and energy, some spark or catalyst that we don't understand. It might mean Earth's biosphere is far rarer and more precious than we imagined. But the scariest possibility for others is the opposite. What if Europa's ocean teems with life? What if billions of years of chemical evolution have produced not just microbes but complex ecosystems, sophisticated biochemistry, or even forms of organization we haven't imagined? First contact with an alien biosphere would force humanity to confront profound questions about our significance in a universe that might be extensively alive. Consider the temporal scales involved. If life emerged in Europa's ocean early in solar system history, it would have had over 4 billion years to evolve and diversify. That's longer than complex life has existed on Earth. Europa's hypothetical biosphere might be ancient, mature, and far more sophisticated than we're prepared to discover. The morphology of Europa's potential life forms remains entirely speculative, but the environment imposes certain constraints. No photosynthesis means no plant-like primary producers creating the biomass that supports most of Earth's ecosystems. Instead, chemosynthetic organisms would form the base of any food webs, clustering around energy sources and potentially creating very different ecological structures. Mobility in Europa's ocean would depend on the physical environment. If the ocean is well mixed by convection or other processes, organisms might need to be free-floating or capable of active swimming. If chemical gradients are stable over time, life might be more sessile, attached to surfaces where favorable conditions persist. The absence of seasonal cycles, day-night rhythms, or climate variation might create very different evolutionary pressures than Earth's dynamic surface environments. Europa's life might be incredibly stable and conservative, or it might have evolved sophisticated biochemistry to exploit subtle variations in chemical availability. But speculation must yield to observation. Europa Clipper will provide our first comprehensive assessment of whether Europa can support life. The mission might not find organisms, but it will determine whether we should be looking for them. And that determination, whether Europa is habitable or sterile, will reshape our understanding of life's potential throughout the cosmos. The silence of Europa's ocean might be the silence of a sterile world. Or it might be the silence of ecosystems so alien we don't yet know how to hear them. Part 12. Lessons from Earth, Antarctica's Hidden Lakes. 800 meters beneath Antarctica's ice sheet, in conditions that would seem alien to most Earth life, Lake Whillans hosts a thriving microbial ecosystem. No sunlight has touched these waters for thousands of years. The temperature hovers near freezing. The pressure is crushing. Yet when scientists first drilled into the lake in 2013, they found not sterility, but abundant life. This isn't contamination or wishful thinking. Rigorous sterile drilling techniques confirmed that Lake Whillans and other subglacial lakes contain indigenous microbial communities that have adapted to extreme conditions remarkably similar to what we might find beneath Europa's ice. These hidden ecosystems survive entirely on chemosynthesis, harvesting chemical energy instead of sunlight. The microbes in Lake Whillans feed on rock-derived chemistry. As the ice sheet flows over the underlying bedrock, it grinds minerals into fine particles that dissolve into the subglacial water. The resulting chemical cocktail includes sulfates, nitrates, and organic compounds that microorganisms can use for energy. It's life powered by geology rather than photosynthesis. Lake Mercer, sampled in 2018, revealed even greater biological diversity. The lake's sediments contained not just bacteria, but complex organic compounds and evidence of sophisticated metabolic processes. Some organisms appear to use iron compounds as electron acceptors, creating reducing conditions that would be toxic to most surface life, but provide energy for specialized chemosynthetic bacteria. These Antarctic discoveries revolutionized our understanding of life's limits. Before the subglacial lake expeditions, many scientists assumed that permanent darkness, freezing temperatures, and isolation from surface nutrients would create sterile environments. Instead, these conditions fostered unique ecosystems that demonstrate life's remarkable adaptability. The parallels to Europa are striking, but not perfect. Antarctica's subglacial lakes exist under hundreds of meters of ice, while Europa's ocean lies beneath tens of kilometers. Earth's hidden lakes are relatively small and shallow compared to Europa's global sea. The chemistry differs significantly. Earth's lakes are fed by rock weathering, while Europa's ocean might be influenced by hydrothermal venting and radiation chemistry. Yet the fundamental principle remains. Life can thrive in permanently dark, ice-covered environments using only chemical energy sources. Antarctica's subglacial ecosystems prove that sunlight isn't essential for biological activity, that microorganisms can extract energy from mineral-water interactions, and that ice-covered environments can maintain stable conditions suitable for life over geological time periods. The diversity found in places like Lake Whillans also challenges assumptions about extreme environment ecosystems. Rather than hosting just a few hardy survivor species, these hidden lakes contain complex microbial communities with different metabolic strategies, ecological niches, and interactive relationships. If Antarctica's relatively small subglacial lakes can support such diversity, Europa's vast ocean might host ecosystems of stunning complexity. The research techniques developed for Antarctica's subglacial lakes directly inform Europa exploration strategies. Clean drilling protocols, sterile sampling procedures, and contamination detection methods pioneered in Antarctica will be essential for any future Europa landing missions. The lessons learned from accessing Earth's hidden biospheres provide blueprints for responsibly investigating alien ones. But Antarctica also highlights the challenges of detecting life in extreme environments. Many of Lake Whillans' microorganisms are present in extremely low concentrations, requiring sensitive analytical techniques to identify. Some organisms grow so slowly that detecting their metabolic activity requires weeks of careful observation. Europa's hypothetical life might be similarly subtle and challenging to detect. The discovery process in Antarctica involved years of careful site selection, technological development, and multiple expeditions before achieving breakthrough results. The first attempts to sample subglacial lakes were contaminated or technically unsuccessful. Success required persistence, improved methods, and sophisticated analytical techniques. Europa exploration will likely follow a similar pattern of incremental progress and technological refinement. Climate records from Antarctic ice cores show that these subglacial ecosystems have persisted through dramatic climate changes over millions of years. The ice cover provides thermal stability that buffers the lakes from surface temperature variations. This stability might be even more pronounced on Europa, where the ice shell could maintain ocean conditions over billions of years. The energy budgets of Antarctic subglacial ecosystems are instructive for astrobiology. Lake Whillans receives chemical energy equivalent to only about 1% of what reaches Earth's surface through photosynthesis, yet this minimal energy flux supports active biological communities. Europa's chemical energy sources might be similarly limited, suggesting that alien ecosystems could persist on energy levels far below what drives Earth's surface biosphere. Antarctica's subglacial lakes also demonstrate how isolated ecosystems can diverge from surface life. Some microorganisms in these lakes have evolved metabolic pathways not found in surface environments, adapted to chemical conditions that don't exist elsewhere on Earth. Europa's 4 billion-year isolation might have produced biochemistry that's even more divergent from familiar life forms. The psychological impact of Antarctica's discoveries shouldn't be underestimated. Finding abundant life in Earth's most isolated and extreme environments changes how we think about habitability throughout the solar system. Every ice-covered moon becomes a potential habitat. Every subsurface ocean becomes a candidate for biological activity. Yet Antarctica also teaches humility about the challenges of life detection. Even on Earth, with direct access to samples and sophisticated laboratory facilities, confirming the presence of life in extreme environments required years of careful work. Detecting life on Europa, if it exists, will be far more difficult and will require technologies and techniques we're still developing. The hidden lakes beneath Antarctica's ice prove that our planet's biosphere extends far beyond the sunlit surface environments that dominate our imagination. They show us that life is opportunistic, adaptable, and capable of thriving in conditions we once thought prohibitive. Most importantly, they provide concrete examples of the kinds of ecosystems that might exist beneath Europa's ice, transforming speculation about alien life into informed scientific hypotheses based on Earth's own hidden biosphere. If Antarctica can sustain life beneath its ice, Europa's far larger and more stable ocean might host ecosystems that make Earth's subglacial lakes look impoverished by comparison. Part 13. The Human Touch. Messages, Art, and Meaning. Etched in titanium aboard Europa Clipper, poet Ada Limon's words accompany humanity's most ambitious search for life beyond Earth. O second moon, we too are made of water, of vast and beckoning seas. The poem, In Praise of Mystery, a poem for Europa, transforms a scientific instrument into something deeper, a cultural bridge spanning the void between worlds. This isn't just sentimental decoration on a research mission. The poem, engraved on the spacecraft's radiation vault, represents humanity's recognition that the search for life is fundamentally about understanding ourselves. We're not just investigating Europa's habitability, we're exploring what it means to be alive in a universe that might be filled with other forms of consciousness. NASA's Message in a Bottle campaign added another layer of human connection to the mission. Over 2 million names are etched on microchips mounted alongside Limon's poem, creating a literal passenger manifest of human curiosity. Children who submitted their names will be adults when Clipper arrives at Jupiter, carrying their childhood dreams into the outer solar system. The vault plate serves dual purposes, protecting the spacecraft's electronic heart from Jupiter's lethal radiation, while carrying humanity's artistic expression toward an alien world. There's profound symbolism in using the same metal shield that guards against cosmic destruction to preserve human creativity and wonder. The poem will survive conditions that would kill its author in minutes. But this artistic cargo raises profound questions about representation and meaning. If Europa harbors life, what will alien biochemistry make of human poetry? The question misses the point. The poem isn't meant for hypothetical Europa life forms. It's meant for us, a reminder that scientific exploration is inseparable from human meaning-making, imagination, and the creative impulse that drives us to reach beyond our origins. Le Mon's verses capture something essential about the Europa mission. What we name memory is the deepest current. What we name love is the undertow. We're exploring Europa not just for scientific knowledge, but because the search itself defines us as a species. The mission embodies our refusal to accept the limitations of terrestrial existence, our compulsive need to know what lies beyond the next horizon. The public engagement surrounding Europa Clipper demonstrates space exploration's unique power to inspire collective imagination. Launch events drew millions of viewers. Educational programs reached students across continents. Social media campaigns made Jupiter's moon a household name. The mission succeeded in capturing public attention because it addresses humanity's most fundamental question: are we alone? Consider the temporal symbolism. The poem will travel for nearly 6 years before reaching Jupiter, then spend years studying Europa before the mission ends. By the time Clipper completes its investigation, the children who submitted their names will be establishing careers, starting families, and shaping the world's response to whatever the mission discovers. The spacecraft carries not just their names, but their generational stake in the search for life. If Clipper finds evidence of habitability, or even hints of biological activity, the global conversation will intensify in ways we can barely imagine. Religious communities will grapple with theological implications of alien life. Philosophers will debate consciousness and intelligence beyond Earth. Scientists will redesign research priorities around astrobiology. Artists will find new metaphors for existence in a populated universe. The poem aboard Clipper acknowledges this transformative potential. We too are made of water, of vast and beckoning seas. We too are made of wonders, of great and ordinary loves. The search for Europa's life is simultaneously a search for our own significance. Finding biology beyond Earth wouldn't diminish humanity. It would place us within a cosmic community of living worlds. But the artistic dimension of Europa Clipper serves another crucial function. It humanizes an otherwise technical endeavor. Space exploration can seem abstract, dominated by engineering challenges and scientific objectives that feel remote from daily experience. Poetry makes the mission personal, connecting individual human experiences to cosmic exploration. The choice of Ada Limon as the mission's poet wasn't arbitrary. Her work consistently explores themes of connection, wonder, and humanity's relationship with the natural world. Her Europa poem extends these themes beyond Earth, imagining kinship with alien environments and potential life forms. It's environmental poetry on a cosmic scale. There's also practical symbolism in carrying human art to Jupiter's radiation environment. The poem will survive exposure to particle bombardment that would destroy biological tissue, digital storage media, and most human artifacts. In choosing titanium engraving, NASA ensured that human creativity would outlast human biology in one of the most hostile environments in the solar system. The Message in a Bottle campaign created unprecedented personal investment in a space mission. Unlike previous missions carrying golden records or plaques for hypothetical alien recipients, Europa Clipper carries names specifically for human participants. The spacecraft becomes an extension of everyone who contributed, a technological avatar carrying human presence to worlds we cannot physically visit. This personal connection will intensify when results start arriving in the early 2030s. Every discovery, ice thickness measurements, chemical detections, possible plume observations, will feel personally significant to the millions who sent their names toward Europa. the mission transforms passive public interest into active participation in exploration. The artistic and cultural dimensions of Europa Clipper acknowledge that the search for life beyond Earth is ultimately a humanistic endeavor. We explore not just to gather data, but to satisfy curiosity, wonder, and the creative impulse that makes us distinctively human. The poem accompanying our search for Europa's life celebrates the qualities that drive us to seek life elsewhere: imagination, empathy, and the recognition that intelligence anywhere in the universe might share fundamental experiences of consciousness and connection. In etching poetry onto our most sophisticated astrobiology mission, we declare that the search for life is inseparable from the search for meaning, beauty, and understanding that defines human culture at its best. Part 14. The Terrifying Future, Lander, Cryobot, and Ethics. Europa Clipper is just the beginning. If the mission confirms Europa's habitability, it will unleash a cascade of increasingly ambitious and ethically complex follow-up missions that could fundamentally alter humanity's relationship with alien worlds. We're potentially on the threshold of the most consequential moment in human history, and we're terrifyingly unprepared for what comes next. The Europa lander remains a concept study, but one that grows more compelling with every piece of evidence suggesting Europa's ocean could support life. Picture a spacecraft designed to survive Europa's radiation environment while drilling or scooping samples from the near-surface ice. The technical challenges are staggering: power systems that function in permanent shadow, electronics hardened against radiation doses that would sterilize Earth's surface, and sample handling systems that can detect biological signatures in materials that have been bombarded by high-energy particles for millennia. But technical challenges pale compared to the ethical minefield of actually touching Europa's surface. Every landed mission carries the risk of contamination, introducing Earth microorganisms to an environment that might host indigenous life. The consequences could be catastrophic. Earth bacteria could potentially outcompete and destroy alien ecosystems that took billions of years to evolve. Current planetary protection protocols classify Europa as a Category 3 target for flyby missions and Category 4 for landed missions. These designations require increasingly stringent sterilization procedures designed to keep the probability of forward contamination extremely low. But extremely low isn't zero, and the stakes couldn't be higher. The requirements stem from international agreements coordinated through the Committee on Space Research and implemented through NASA's planetary protection standards. Every component of a Europa lander would require heat sterilization, radiation treatment, or chemical cleaning procedures that add complexity, cost, and failure modes to an already challenging mission. Consider the impossible trade-offs. The cleaner we make our spacecraft, the more likely we are to destroy or compromise the very instruments designed to detect life. Sterilization procedures can alter sensitive surfaces, degrade organic chemistry detection capabilities, and introduce contamination from the cleaning processes themselves. We're trying to build sterile life detection systems using techniques that might make life detection impossible. Even more ambitious is the concept of a cryobot, a nuclear-powered probe designed to melt through Europa's ice shell and reach the ocean below. The engineering challenges border on science fiction. A self-guided thermal drill that can navigate tens of kilometers through ice while maintaining communication with Earth, avoiding obstacles, and preserving samples for analysis. The power requirements alone would demand nuclear systems more sophisticated than anything currently deployed in space. Navigation presents particular nightmares. How does a cryobot determine its location while buried in featureless ice? How does it avoid getting stuck in debris or veering off course? How does it maintain a communication link with the surface through dozens of kilometers of ice and water? These aren't just technical problems, they're fundamental challenges that might require entirely new approaches to robotics and autonomous systems. But the contamination concerns for a cryobot mission are even more severe than for surface landers. A probe that directly contacts Europa's ocean, would introduce Earth materials to the most potentially habitable environment in the solar system. Even if the cryobot itself were perfectly sterile, an impossibility given current technology, the heat generated by melting through the ice could alter the chemical environment and disrupt potential ecosystems near the penetration site. The planetary protection community grapples with questions that have no easy answers. What level of contamination risk is acceptable when balanced against scientific knowledge? Should we delay exploration until we develop better sterilization techniques? How do we protect potentially indigenous life while still investigating whether it exists? Some researchers argue for biologically reversible exploration, missions designed to minimize impact while maximizing scientific return. This might mean staying on the surface until we understand Europa's biology better, or developing sample return missions that bring materials back to Earth for analysis in controlled laboratory environments. But sample return raises its own terrifying possibilities: backward contamination. If Europa hosts life forms that could survive in Earth's environment, returned samples would require quarantine procedures that make current biosafety protocols look primitive. We might need to build entire laboratories in space or underground facilities that can contain potentially alien biological materials. The timeline for these advanced missions stretches across decades. Even if Europa Clipper confirms habitability and identifies optimal landing sites, developing and deploying follow-up missions will require 10 to 20 years of additional technological development. Current space mission planning operates on scales that span entire careers, entire generations of scientists and engineers. Yet the pressure to move quickly will be enormous if Clipper finds compelling evidence for habitability. Public enthusiasm, scientific competition, and international prestige will drive demands for rapid follow-up missions. The tension between responsible exploration and public expectations could create dangerous shortcuts in planetary protection protocols. International coordination adds another layer of complexity. Multiple space agencies are developing Europa mission concepts, but planetary protection standards vary between countries. What happens if one nation's Europa mission contaminates the environment before others can investigate? Who has the authority to regulate access to potentially habitable worlds? The legal framework for protecting ocean worlds barely exists. The Outer Space Treaty prohibits harmful contamination of celestial bodies, but it doesn't define harmful or specify enforcement mechanisms. As multiple nations develop capabilities to explore Europa, the absence of clear international protocols becomes increasingly dangerous. Perhaps most unsettling is the possibility that we're approaching this threshold without adequate preparation for success. Our planetary protection protocols were developed for worlds we assumed were sterile. Our space law was written for an era when life beyond Earth seemed purely theoretical. Our international coordination mechanisms struggle with missions that could affect humanity's understanding of life itself. The terrifying reality isn't just that we might find life on Europa, it's that we might destroy it before we understand what we've found. The same technological capabilities that allow us to explore alien worlds also give us the power to irreversibly alter them. We're wielding tools of unprecedented reach and power with protocols designed for far simpler challenges. Yet the alternative, not exploring Europa despite evidence of habitability, seems equally untenable. If life exists in Europa's ocean, studying it could revolutionize biology, medicine, and our understanding of intelligence throughout the universe. The potential benefits of contact with alien biology might outweigh the risks of contamination, especially if we develop sufficiently sophisticated protection protocols. The future of Europa exploration will likely unfold through careful incremental steps, orbital surveys followed by surface reconnaissance, sample analysis preceding direct ocean access. Each phase will inform the next, building knowledge while minimizing risks. But each phase also commits us more deeply to a path that could lead to humanity's first contact with alien life. The terror isn't really about finding monsters or hostile aliens. The terror is about responsibility, the awesome burden of being the first species in the history of life on Earth to potentially encounter biology from another world. We're not just exploring Europa, we're potentially becoming cosmic gardeners, responsible for protecting and nurturing life that might be far older and more precious than our own. Part 15. The greatest question: are we alone? There are only two possibilities, and both are equally profound. Either Europa harbours life, suggesting that biology emerges readily wherever conditions allow, or Europa is sterile, implying that Earth's biosphere might be a cosmic anomaly of staggering rarity. Either answer would fundamentally reshape humanity's understanding of our place in the universe. Consider the implications of finding life. If Europa's ocean hosts even simple microorganisms, it would represent the second independent emergence of biology in our solar system. Two Genesis events in one stellar system would suggest that life isn't a miraculous accident, but a predictable consequence of appropriate chemistry, energy, and time. The universe would transform from a vast sterile wilderness into a garden teeming with potential biospheres. The statistical implications cascade outward at incomprehensible scales. Our galaxy contains roughly 400 billion stars, many with planetary systems that include ocean worlds. If life emerges readily in subsurface seas, then Europa's discovery would suggest billions of potentially inhabited worlds within the Milky Way alone. The cosmos might be alive with biology we're only beginning to imagine, but the alternative is equally transformative. Europa's sterility would hint at Earth's profound isolation. If a world with all the apparent ingredients for life remains lifeless, it would suggest that biology requires something beyond chemistry and energy, some spark, catalyst, or sequence of events so improbable that it might occur only once in billions of worlds. We might be far more alone than we ever dared fear. Europa Clipper will provide crucial data for this cosmic question, though not a definitive answer. The mission will determine Europa's ocean depth and salinity, map the ice shell structure, characterize surface chemistry, assess energy sources, and evaluate the stability of conditions over geological time. This comprehensive habitability assessment will tell us whether Europa could support life, not whether it does. Yet even negative results would be scientifically revolutionary. If Clipper finds that Europa lacks essential ingredients, if the ocean is too acidic, the energy sources too sparse, or the environment too unstable, it would constrain models of habitability throughout the solar system. We'd learn not just about Europa, but about the fundamental requirements for biology anywhere. The mission timeline itself reflects the patience required for cosmic questions. Clipper arrives at Jupiter in 2030 and conducts its multi-year survey through the mid-2030s. Major discoveries might unfold gradually as data accumulates, analyzed, and interpreted. We're talking about a decade-long process of revelation that will span multiple presidential administrations, economic cycles, and technological generations. But Clipper's results will set the stage for everything that follows. If Europa appears habitable, it will justify the enormous investments required for lander missions, sample return, or eventual direct ocean access. If Europa appears sterile or hostile to life, attention might shift to other ocean worlds like Enceladus, Ganymede, or Titan. The broader search for life in the universe will also be influenced by Europa's story. Upcoming space telescopes will soon begin detecting atmospheres around Earth-like exoplanets, searching for biosignatures that might indicate biological activity on worlds many light-years away. Europa's results will inform how we interpret those distant signals and assess the likelihood of life throughout the cosmos. Within our lifetimes, we might witness a fundamental transition in human understanding. The generation now being born could grow up in a universe known to host multiple biospheres, or in one where Earth's life appears uniquely precious and isolated. Either revelation would reshape philosophy, religion, science, and culture in ways we can barely anticipate. Religious communities worldwide are already grappling with the theological implications of potential alien life. Some traditions embrace the possibility as evidence of divine creativity on cosmic scales. Others struggle with doctrines centered on humanity's unique relationship with creation. The discovery of Europa life would accelerate these theological conversations and potentially reshape spiritual beliefs for billions of people. Scientific priorities would shift dramatically toward comparative biology and astrobiology. Understanding how Earth life relates to Europa life, whether they share common chemistry, similar metabolic strategies, or entirely alien approaches to biological organization, would become central research questions. We might need to develop entirely new scientific disciplines to study alien biochemistry. Cultural impacts could be equally profound. Art, literature, and popular culture are already inspired by the possibility of Europa life. Confirmed discovery would unleash creative responses across all human media as artists grapple with humanity's place in a populated universe. Our stories about ourselves, our origins, and our destiny would require fundamental revision. But perhaps the most unsettling aspect of approaching this threshold is our complete inability to predict its consequences. Human history provides no precedent for contact with alien biology. Previous transformative discoveries, evolution, DNA, quantum mechanics, relativity, revolutionized specific fields of knowledge. The discovery of extraterrestrial life would revolutionize everything. The question, "Are we alone?" has driven human curiosity for millennia, inspiring mythology, philosophy, and science across all cultures. Europa Clipper represents our best current effort to answer this question through direct investigation rather than speculation. We're moving from wondering about alien life to actively searching for it with instruments capable of detecting its signatures. Yet Europa forces us to confront the possibility that life might be far stranger than we imagine. 4 billion years of independent evolution in conditions unlike anything on Earth could produce biochemistry, organization, and possibly even intelligence that challenges our basic assumptions about what life can be. We might not recognize Europa biology even if we encounter it directly. The timeline ahead stretches across decades of exploration, analysis, and follow-up missions. Today's children will be adults when we have definitive answers about Europa's habitability. Today's students will be senior scientists when we potentially make direct contact with alien biology. We're embarking on a generational journey toward one of the most profound discoveries in human history. Arthur C. Clarke's fictional warning, "All these worlds are yours except Europa. Attempt no landing there," has become our scientific mandate. We approach Europa not as conquerors but as careful investigators, recognizing that what we find might be far more precious and significant than gold, oil, or any terrestrial resource. The more we learn about Europa, the less it feels forbidden, and the more it feels sacred. Not mystically sacred, but sacred in the deepest scientific sense. A place that might preserve the record of life's emergence in our solar system. A world that might demonstrate biology's cosmic potential. An alien ocean that might be humanity's first contact with the living universe beyond Earth. We stand on the threshold of potentially answering the greatest question our species has ever asked. And the terrifying beauty of that moment is that we have absolutely no idea what the answer will be.